So, couple things, right? Exam next Wednesday is the plan, right? Just gotta do it, get it over with, and then after spring break it'll be clean break. We'll wash our hands of MATLAB, and then for the time being, and then we'll dive into MathCAD. We'll have maybe a couple weeks with MathCAD.
Do we have access to MathCAD on our personal?
No, but we'll cover that next time. You have to be able to you have to go in, you have to log into those remote computers. Because they actually have a license, but they don't let you put it on personal computers. You can put it on university-owned computers, but you can't put it on personal computers. So we have to log into the remote stuff, that remote lab. And so we'll cover all that next week. And so we'll do a couple weeks of MATLAB or MathCAD, and then we'll just do like a quick survey of all these other programs. And each class will just be showing those things, and then showing you what you can do with it, and showing you what ChatGPT could do with it, and stuff like that. So then you might be wondering where the last homework is. Right? It's coming. We're in the process of last MATLAB homework. I'm working on it. You okay, Kira? I was like, where did Kira go? He disappeared. So I'm working on it. I was originally going to be like, okay, I'm not going to do what we're going to cover today. I was like, I made up my mind. I was like, we're not going to do it. And then I looked at my homeworks, and this last homework is just beautiful. One of the best works of my life that I put together. This homework of it was so cool. It is so cool. And so I had this moment of like, what do I do? Do I teach this stuff? Do I not teach this stuff? Do I, and then if I don't teach it, then we can't do it. And so then I was going back and forth, and I reworked the homework a few times, and I was like, screw it, I'm teaching it. So I'm going to teach it, and then we're going to do some examples with it today, right? And then I'm going to have you solve a simpler program, a simpler thing using this method. Okay? And then you're going to solve it numerically, and then you're going to solve it symbolically, and you can compare the two. We're going to do exactly what we're doing today. You'll do that for your homework. But then the hard part, the really cool problem I was talking about, I'm going to make that an extra credit. That if you want to go on and do this extra credit problem, you can. And so it's up to you on whether or not you want to dive in and do the super cool one. The super cool one is super cool. It's super cool. And last time, at least 2 years ago, ChatGPT could not do it, so you had to dive in and do it yourself. So, okay. So what we're gonna do, Kyle. Don't tell Kyle what we just talked about. You missed it. Okay.
Sure, it'll be on the YouTube recording.
That's a good point. Okay, so what we're gonna cover is, and this is the part that I struggle with, is we're gonna use these ordinary differential equation solvers in MATLAB, right? Again, I'm sorry, I don't know how to do. I'm sorry. No. Oh yeah, glasses today. Okay, now I don't know, and so we're gonna cover this thing called anonymous functions first, right? And then we're gonna build up and show you how to use these differential equation solvers in MATLAB. Those of you that were in structural dynamics, we made our own, but when we did the central difference method for solving the thing, that was actually using, that was a differential equation solver that we made. They have built-in equation solvers within, and so we're gonna use the built-in solvers in here, and I'm gonna show you how to use those things. We'll do a couple examples with that today. Okay, so there's this thing called anonymous functions, okay? They're just like regular functions, but you define, I think they used to be called inline functions. Instead of putting them down at the bottom of your thing, you actually just put them right into this. So here's a little, we'll type this one out. All right, so if I come, what do I do this? I'm gonna do this right here. Okay, I come in here, and then I say, I'm gonna make a new function called square, not square root, but just square, and that's gonna be equal to, and what you do is you put this at symbol, and you're gonna say it's gonna be a function of, or I guess a function x, and then you call that x dot to the second. So what this does is it turns, let's see what it does here. Right? It just makes a new function. It says, hey, function, it's a function that's a function of x. And so now I could just do square, and then I could put in 2, and it should just return 4. So instead of defining a function down below, you just say, hey, this is going to be a function of x. That's what the at x does. And then you say what it's going to do afterwards. And so in this case, I just square it, right? And the way that's set up is I can work it like this. I could do square, and I can give it a vector even too. 1, 2, 3, 4, 5, right? I need to do right? And then it'll do that as well, right? And it'll just square each member individually. So that's sometimes you may want to do that. right? You may want to define an inline function like that. If you have these inline functions, there's a whole slew of things you could do with them, right? Yeah, you could do integrals, definite integrals and indefinite, or yeah, I guess they have to be definite integrals. Now, then you could also do these, use these other, by learning how to do these anonymous functions, there's a whole bunch of other things out there. There's a command called fmin confined, so that finds the minimum of a function. You could do fmin search, which is similar. It's not a confined search. You could do fmin unconfined. You could do fsolves. You could do integrals. You could do ordinary differential equation solvers. That's what we're going to use it for today. Okay, we could do the definite integral of a given function using the quadratic method. There's this one called f0, which finds where the function is equal to 0. There's all these different functions that you could use based off of this, okay, once you learn how to define those things. Let's do, well, you can take derivatives of stuff, you take the integrals. So this just kind of shows you if you want to look here, right? So I defined this thing as the square, and then I did the numeric derivative of it, right? So I did the differential, the diff of the square, and I divide by dx. So that's just numerical derivative, and I just plot both of them on there. There's a plot of x squared. So you just made, it's like making your own function. It's just, you just do it in line as opposed to putting it down below, okay? And then this right here, this next stuff is how you find the maximum. So we're kind of demonstrating how to use mins and maxes. So let me just jump over here and make an equation. This is going to show one at play here. So I'm going to make a new function, and I'm going to say it's equal to, I'm going to make it as an x. I'm going to make it a function of x. I'm going to call it x dot to the third minus 3 times x dot to the second minus 24 times x plus 36. Okay, new function that does that. And then I'm going to define my x's. Make my x's go from, I'm going to do a lin space, going from negative 10 to 10, and I say 1,000 spaces. Figure 2, left. We're just going to plot this, plot x comma f of x. Just to show you that, like, so then, before I didn't have to do, like, before I'd have to say what y is equal to, y is equal to all those things, and now you just say f is a function, and I could change it. I could just change what my x is down here, and then it calls the function, and then the function returns the stuff, and these things happen. Okay, so now we got that, and so then you could use this, and you could find the minimums. So you could do this. We'll say this. We'll go x and min. Minimum is equal to, we'll use a command called fmin search. And we're gonna look for f of x, the minimum f, and then we're gonna start at a value of 4. Tells you where you want to start with. Right? And so it went through, right? There's a couple different mins and maxes here, like local. Right? And so it returns to us, right, at x equals 4. Right? I don't know why it's, yeah, I just happened to guess where it was. You give an initial guess, and it returns like, oh, hey, by the way, at x equals 4, right here, right in here, at x equals 4, there's a minimum right there. And you'll notice that that's not the overall minimum, right? It's finding a local minimum. That's why it gives you different options on what you can put in as your initial value. So I just put in 3. So it started out with 3, and then it's searching around in this region right here, and it returns to us the minimum, this local minimum that it finds right here. If I put in a different starting condition, if I put in like negative, well, and there's also, like, clearly it goes down to a negative 1,000, so that just returned that local one, right? And so it kind of gives it some starting and stuff like that. Yeah, right. It'll give you that vicinity. So that's just to show you there's these things built into it, right? The problem that I said to do was to try to find the minimum of this guy, so we'll just kind of I'll change this guy. F is equal to, okay, again, make it as a function of x. And then call this x dot to the second times, or dot times, sine of x. Okay. If you don't put the dot times there, right, it wouldn't work because x squared, right, is going to return a vector, and then you're trying to multiply it by sine, which returns a vector, and it doesn't know how to handle that math, so you have to put the dot there, right? And so if we plot this guy, that's pretty cool, right? So there's a bunch of minimums and maximums built into that. And so if I did the f-min search of that equation, right, and I started out with a 3, right, and it returns to me 5. So right, it found this minimum right here. Okay. So what if I said, actually what the problem statement says down below, if you kind of go in here, it says, find all of the local minimum maximums for the following function using anonymous functions and their built-in functions. Also find all the points where f of x equals 0 is what it says to do. Okay. So if I said, let's just mess around with this. If I was saying find all, anonymous functions, find the local maximum and minimum for the following functions using anonymous functions. Okay, find all of them, right? There's a lot of them, right? There's this one right here. Does it say maximum or minimum? Maximum, minimum. Okay, so if I was trying to find the minimums, for instance, right? There's a minimum here. There's a minimum here. There's a minimum here, right? How do you think you would go about doing that?
F-min bound.
Oh, is there an f-min bound? Yeah, you give it the bounds of it and stuff. I don't think it'll still only return one of them. Right?
Yeah, only gives one.
It only gives you one because it's all based off of this starting point. What do you think a technique you could do if I wanted? What's that? You could do 0. Sure, let's see what happens with 0. Right? That still will only give us 1, right? It found this -2 one, right? Right in here, probably right here. It found that one. Yeah, that's right. You could do a loop, right, and give it different starting conditions, right, and then see what it does. Let's try it. How about you try it? Try to put a loop in here to kind of loop through some different initial starting conditions and see if you can catch all those things, catch all the mins, for instance.
And if you really want, we can make a loop that steps forward if you get the same result, and then you're like slowly stepping through,
Mm-hmm.
and then once it gets a new result, it records it.
Yeah.
And then continues doing
Sure.
the same.
Dude, yeah, you're thinking like it. You're in there, dude. You're in it.
I don't want to do it though.
But yeah, so you could do simpler. I just do brute force. We'll just see what happens here. For equals, let's see, x naughts. Make this thing go from like negative. Well, it'll be the same as x. Oh, you could do the x's. Right, that's too many of them. We're gonna go -10 to 10. 1 to the length of x naughts. X naughts of I. Yeah, I mean, I did it. That's brute force. It works, though, right? We found them all.
Yeah, but you're getting repeated values.
Yeah, get repeated values. You're right. You're right. So you could set it up where you don't, like you said, only save them if it's a new one. You can set it up and only saves it a new one. But it's just brute force if you wanted to look at it. Just setting a loop on that would do it, right? You could loop through each one and just start with a bunch of different starting values, and then it goes through and it plucks out this guy, this guy, this guy, this guy. Okay? You found all of them. Okay? But you're getting to a point now where you probably could code that. You would know what you were doing. Right, Kyle? You can figure it out.
Oh, yeah.
You'd only save the ones that aren't repeats and stuff. And what if, because there's no fmax search. Is there an fmax search? I don't think there's an fmax search.
Mine's not giving me the
No, no fmax search. What do you think you could do if you were after the maxes? Huh? It's a quick little hacking.
absolutely no. You like invert the function.
Yeah, just negative, right? Just find the f-min search of the negative of the function. Right? Wouldn't that work? If I just put in if I put in a negative f, find the f min search of negative f, and so it would find the negatives, or the mins would become the maxes. See that?
Yeah, maybe.
And let me do that. Roger this, I'll put it up here then. Put it up here, you son of a bitch. That flipped it there, right? And then that should return the maximum values, right? That's just hacking. That's some hacking for you. Some hacking for you, Noah. Okay. And then F0s is the other one, right? If I wanted to find, same thing. If we change this to F0, it finds everywhere that the function is equal to 0. I think this will do the same thing. Right. Equals 0 at negative 9.4, negative 6.28, negative 3.16, negative 1.9 at x equals 0, and then these other values is and then going up as well. Again, there's just repeats there. Right. So the way that F0 works, same idea. You just it'll find where the function equals to 0, and then you just give it initial starts, and you have to give it a bunch of different initial starts to go. Right. And built behind the scenes. Have you guys ever used in Excel, there's like a goal seek? Have you guys used goal seek?
All the time.
Yeah, right? The goal seek, right? And the goal seek is you come in, you say, I want this cell be equal this by changing this other cell. And then if you ever watch what the answer does, it's just like, it goes over here, and then it goes over here, and then it goes over here, and then it goes over there, and then it's just like comes in on and converges on the answer. It's doing this, right? It has the same type of algorithm built into it. And you know, if you really get into like some real like numerical analysis programs, they go over like what kind of method that F0 uses for like narrowing in on the exact answer, right? There's math behind all of that, right? And it uses different methods. And if you look inside the help for like F0, there's a bunch of stuff you can change. Right? There's all you could change like what techniques you're using. If you look to see, there's options, right? If you look under options down here, you could tell it what method to use and what kind of tolerance you want to use, right? And you could change the different types of solvers that they're using. It gives you a lot of control over like what methods you could use for solving these things. Okay. That one I used a lot because it doesn't have to be like, this is a clearly defined function, right? This is a clearly defined function where it's just like, here it is and here's the output. F0 will work on any, you could have the thing go in and do a full matrix analysis on something and then change this other value and then do all this other things to it and then calculate the moments and shears and stuff like that and then have an output being something, and then F0 can be based off of that, and it'll run and call on that big function every single time, and it'll work its way around. It doesn't have to be just this inline function, but that's what we show you. Okay. So again, you got to be a little creative on what you have as your initial guess, right? Because it only knows to look in that region. It needs to know where to start, and then there you go. Okay. So now let's come down. Let's do ordinary differential equations. So now we covered those are inline functions. We did a bunch of stuff with that, right? And we just did this, found the maximums and minimums. Okay. So differential equations, right? Ordinary differential equations. MATLAB has a whole bunch of methods for solving differential equations, right? I don't know what any of them mean, okay? I don't know the difference between any of them, okay? I mean, here's what their help says. An ODE 45, it solves a non-stiff differential equation. What does that mean? I don't know. Okay? It's with medium order method. Oh yeah, okay, right? Or ODE 23. This is a solve a non-stiff differential equation. Low order method, right? Solve a differential equation with high order method, right? Non-stiff, and then they have these other ones down below, right? We're just gonna ODE 15, ODE 23, S versus 20. I don't know. We're just gonna do ODE 45. Again, don't know the difference between. Now, what's really weird about it, this is that's what this note is about, and we'll do an example here in a second. It's kind of weird how you use these things, right? It cannot handle higher order ODEs, right? It can only solve differential equations that are first order, okay? But those are boring. We don't have a lot of first order differential equations. We have second order, third order, fourth order. That's where things are more interesting, okay? So what it can handle is systems of first order differential equations. So we have to turn any differential equation that we get into a bunch of first order differential equations, right? And so if you have a fourth order differential equation, you need 4 first order differential equations. If we have a second order, you need 2 first order differential equations. And to show you how that works, I have this nice little example. I stepped through every little step here, okay? So this is, I was good to use structures, but I went with fluids.
Cool.
Yeah, fluids. Yeah, and fluids, you can count air as a fluid, correct? Air is a fluid, yep, air is a fluid. Okay, and so this is drag. Okay, so where this is modeling, if you were to model a ball that you held up in the air and you let go of it and it's gonna drop, right? And so as it drops, right, we usually ignore this in dynamics, we ignore drag in dynamics, but there is drag there. The faster the object moves, the more drag there has. And so it should be a function of the velocity, right? So my drag force, right, my drag force is equal to, so a constant B times V. The B depends on what fluid it's traveling through, right? V being the velocity here, okay? So then we look at the net force on an object is given by Newton's second law, right? Is the net force is equal to mass times acceleration, right? And so this ball that's being dropped, it has 2 forces acting on it. As gravity that's pulling down, right? Gravity's pulling down, mass times gravity, that's the force due to gravity right here. And then we have acting in the opposite direction of the movement, opposite direction of gravity going down, so it's gonna be a negative, so in this case, downward is positive, that's equal to minus B times V, right? And so then, so that's our mass of acceleration is mass times gravity minus B times V, okay? Our acceleration is so if x is the position, our acceleration is the second derivative of x, okay? And then our velocity is the first derivative of x, right? That's classic basic dynamics, okay? And then x is the position of the object. So what this becomes is this, right? mx double dot, that's mass times acceleration, equals mass times gravity minus bx dot, right? X dot is the velocity. Right? And so what you do is you just put all the x terms on one side, or you can put everything on the one side. And this is the differential equation that governs how a ball drops, okay? mx double dot plus bx dot minus mg is equal to 0. Okay, that's the differential equation we're gonna solve. So that's a second order differential equation. But again, the problem is MATLAB can't handle, it cannot, with their numeric solvers, solve the second order equation. It can't solve this. Right? Because I need to turn this into 2 first order differential equations. And so this is what you do. And kind of pay attention because you have to do this on your homework. You have to, for the problem that I give you, I think what we're gonna do is vibration, which isn't structures, but it is kind of, because structural dynamics we do it. But that's what it's gonna be. It's gonna be the governing equation for a spring mass damper system is what it is. So it is structures, but it also could be vibrations, but it's not fluids. Now, so
And
that.
are we doing like different damping ratios?
Yeah, and then with a forcing function or not a forcing function. And so you got to pay attention to what we do here. So to turn this into 2 linked first order differential equations, this is what we do. Okay, we say y1 is equal to x. Okay, I've introduced this new variable. Y1 is x. Okay, y2 is equal to the velocity, which is just y1 dot. Okay, so I've introduced y1 and y2. Y1 is just going to be x. Y2 is going to be the derivative of y1. Okay, this is where the linking comes from. Okay, and so then if I come down here after defining these, I substitute these things into my original equation. So I take these and I put them in up here. Okay, so this just becomes my2 dot plus by2 minus mg. See how that's now a first order differential equation, right? Because I've kind of dropped the other differential, because I did this substitution here. So I turned this into a first order differential equation. So what you do at this point is now you solve for y2 dot. So all I did is just algebra to go from this step down to here. So I do y2 dot is equal to mg minus by2 over m, okay? And now there's our system. There's our system of differential equations. It's y1 dot, the derivative of y1 dot is equal to y2, and y2 dot is equal to mg minus by2 divided by m. So it's a coupled system of first order differential equations. is what this is, okay? And so then what we do with MATLAB is, come down here. We have to make a function that is these two linked systems. Okay, so let's do that really quick.
Yes, sir.
Okay, so let's enter it. So we make a new function. This will be like an inline function down at the bottom. It's not using a it's going to return dy, and that's equal to, we'll call this falling object. Falling object. Okay, it's going to be a function of t. It's going to be a function of y. It's going to be a function of m. It's going to be a function of b. It's going to be a function of g. By the way, I don't know if we ever talked about this. When you make functions, you can make it be as many variables as you want, right? We always did it with like a function of one variable, but you can make it a function of all these things, right? It's going to be a function of time. It's going to be a function of y, which we'll get to in a second. It's going to be a function of mass. It's going to be a function of that constant b and the constant g times gravity. Okay, and then what it's going to do, what we want this function to do is we're going to say dy1, so that's the first derivative of 1, it's going to be y2, and then dy2 is equal to what we had before. It's m times g minus b times y2. This is y1 and y2 just become like this y sub 1 and y sub 2. Divided by m. There's my inline function. Right, so basically, I mean, this is this, right? dy1, just put a d in front of it, dy1 is equal to y2. So that's what this is. dy1 is equal to y2. You just put them in subs like that. And then you say dy2 is equal to this. So the dy, that's just this equation. dy2 is just mg times minus by2. Just make sure it can be by2 divided by m. So now those differential equations are entered in there. Okay. Then to do this, we have to give it some values. I need to say what its mass is. Let's say it has a mass of 1, a b, our parameter there. That's just the drag coefficient. That's 0.1. G is equal to 9.81. Okay. I need to give it some initial conditions. And let's say that it's starting out with 0 for a location and 0 for its velocity.
ODE 45.
Yep, I'm going to use ODE 45.
My baby.
Yeah, just put this in. This is 0 velocity, or 0 displacement and 0 velocity. Because you have to give it some initial conditions. We have to give it a time span, t-span. Go from 0 to 10 seconds. Okay, now we're ready to go to our OD45. So the output of that is going to be, it's going to spit out to us t and y. Y being our answer, t being what it chose for time. It's going to be time is going to be between 0 and 10. Has to be between 0 and 10. And then what we do is we say ODE 45. And then you have to do this anonymous thing. You have to do this one thing up at the beginning. You have to say, what we're doing it is of the falling object. We're trying to solve the falling object differential equation, but we have to put in this and say, right, we want this thing, because the reason we have to put in this t comma y thing right here, this at t comma y, is that falling object is actually a function of t, y, m, b, and g. And so we have to tell it, what are we trying to solve it for? And we're trying to solve y in terms of time. So we're telling it that that's what's changing in here, t and y. So then we do that, and then we're going to put in falling object. Then we're going to do calling out t, y, m, b, g. And so it's feeding it t, y, m, b, and g. And then we have to give it the t-span. That's its it's what range are we looking for the solution for? We're going to give it its initial conditions. So you can see down here, right, it says ODE 45, it wants the function, it wants the span, it wants its initial conditions, that's what Y naught is, and then it wants options. You could change, again, all sorts of options. You could tell it which method you want it to use and all sorts of stuff, right? And we're just gonna use the default. So we're gonna end right after initial conditions here. Right? And then that should run. Didn't. Oh, I misspelled initial conditions. Initial conditions. What would it do now?
Your initial conditions need to have this guy here has to be a
Comma.
not a comma, a semicolon.
No.
That makes it a comma vector. That's what it is in your notes.
Oh, I did put a. I did a semicolon there. Oh yeah, I need to make that.
Does that make it a column?
Yeah.
Separates it as columns instead of.
These are the classic.
I mean, mine also isn't working, so I don't know if that's the problem.
25, all right, T and Y, falling object, T, Y, M, B, G.
T space. Should that be a range rather than?
T span, no, 0 to 10.
Was it 0 to 10 or just
Well,
like
should there be a colon, not a comma there? Make it 0 to
Yeah,
10?
I'm looking at my notes. I had this working this morning. Let's see here. And T, Y. Mention falling object must return a column vector.
I'm getting moved to
Did it.
You did it. What did you do?
Well, I just flipped it. But I just want to see if this is right, though. That's what I did. So it really only, it was returning it row vector, and that this I just transposed it. I just added that term to transpose. I flipped it on its side. But why? Now let's see if that gave us the right answer. I don't know why it did that. Okay, so let's just see if it worked here. Let's plot it. Plot T, comma, Y1. Nope. Did yours plot anything?
Does it need to be plot T, Y, two dots?
Well, hold on. She broke down on me. I fucking hate .mlx files. Oh, here it. Yeah. Let's try this too. Stop. I don't, what? Why? I got it working. Let's just see here. don't know why it's making me.
Yeah, I know that.
I don't know why it's making me flip it on its side. Let me double check let me double check this here real quick. We got
I know how to fix it.
yours or mine?
Mine, I'm gonna give it to ChatGPT.
M is 1, B is this, G is 9.81. Additional conditions 0, 0. T and Y, falling object, T, Y, M, B, G, T span, initial conditions, and I'm trying to plot TY1. These look like I got rid of my graphs in here. Did I put any graphs? I didn't put any graphs in there. Look at this. Here's my previous, like the. I want to go 0 to 40. Let's see if this does it. What it's supposed to be doing. Yeah, that's doing what it's supposed to be doing. Okay. See, this is what I did this morning. Look at this one. What's different with this one? M, B, G, initial condition 0, 0. Oh, 0.4. But that doesn't mean that I didn't flip it this morning. See, like back here, right? Let's see if I did. I said initial conditions this, T spans this. O to E45 at T, Y, dropped ball, T, Y, M, G, B, T span, initial conditions. All right, come over here. And my function down here at the bottom, dy is dropped ball, T, Y, M, B, G, dy1, y2. Oh, I do flip it. Look at that, I did flip it. I did flip it. So you do gotta flip it. For some reason, you gotta flip it. You're flipping out. You're flipping out. Huh?
Your homework, we're not going to be supposed to flip it. We're
Yeah,
going to
you're not gonna have. Yeah, but I'm pretty sure you will. So I had to flip it. It wanted it in a column vector versus a row vector. For whatever reason, it wants to do that. You could fix it. So basically, this sets the 1, and then it 2, and then it just flips it on its side. I think you could fix it by. You could put a colon. You could just do it. You could do a 1, 1:1 and a 1:2 there, and it would do the same thing. Anyways.
ChatGPT has it initializing dy as zeros 2, 1, so like makes the thing in the column more.
Already puts it in the column form. Yep. Okay. And so, anyways, let's come back to this. So the first thing, when I'm plotting it right here. Oh my God. So there it is. I mean, that's the answer. That is what that is as time goes on, its position when you let go of it. And so when I plot just y1, your answer comes back. There's 2 columns to it, right? There's y1 and there's y2. It's all the rows in first column. All the rows in first column is my position as a function of time. All the rows in the second column is my velocity, right? The way that we defined this, right? The way that we defined this over here, right? That y1 dot, the derivative of y1 dot is y2, and y2 is the velocity, right? y2 is the velocity. That's where it's more interesting to see. If you drop a ball, if we plot y2, right? That's a plot of the velocity. Oh my God, it keeps. I hate. Does anybody else run into that, like where the plots are weird when you have a .lmlx file? Like sometimes it plots it, sometimes it doesn't plot it. No.
Usually close it.
Close it.
Reopen
And then,
it.
yeah. It's just it still has some bugs. So notice what our velocity does, right? Just as we're talking physics here, right? Our velocity starts out like this, and then it starts peaking out. Why does it start peaking out? Terminal velocity. Isn't that cool? That's the whole point of doing this one, just to show you the turbulent velocity. That's kind of cool, right? When they talk about turbulent, it asymptotically approaches a certain value, right? Because when you hit a point where the pressure coming up from below is equal to mass times gravity, and so that it just hits a constant velocity, and they'll carry down at a constant velocity, and it shows up. So that you can tell that that's the correct answer because it did that. So that's the ODE solver, right? Just to show you, I think I did this in my other one. Tick and talk. Let's just show you that how quickly it solves a second order differential equation in 0.007211 seconds. Ethan, are you impressed by that? That's okay, big guy. How fast is yours?
Mine's faster.
No, it's not.
0.0036.
Yeah, run it a few times. Yeah.
Oh,
7.2. Slow.
I just.
slow. It's not stopping.
And why isn't it stopping?
Infinite loop.
Oh.
Not fast enough. Not fast enough. Not fast enough. Slow.
That's a lie.
No, you know why mine's faster?
I did zeros to initialize
Oh, you did.
initially matrix
Oh, you made a new.
in the function.
It was funny.
What's that?
because it was. Thank you for reminding me. So I gave it to Tim. I was like, "Here, go," and then he goes, "Oh man, mine is way slower."
How much?
I mean, it took him like 60 seconds to run it, and mine was like 0.0072. Like, it was like it was way different. It was quite pleasant. He's like, God, my computer sucks. Mine took like 60 seconds. And then he tried it again and again and again. I was like, and then what's really nice, the way I had it written, like, you could see what my inputs were, so you could tell that I put in the exact numbers that he did, and mine took 0.007, and his took like 60 seconds.
Did he ever figure it out?
Yeah, I told him. I was just like, because he was feeling sad. And so I was like,
And then when he fixed it, was it pretty comfortable with yours? Did you guys
no, I was still 10 times faster. Isn't that crazy? Mine's an M4 chip, and his is an M3 chip.
Even after you had the
10
same
times.
conditions.
10 times the difference. Mine was like 0.00, and his was 0.0, whatever it was. Yeah. And we extended it longer.
It was 0.0 seconds versus.
Yeah. And so we kept doing. We did it a couple of times, and it was about 10 times the difference just between an M3 and an M4 chip, which is crazy. And then I did mention to him that how it was it was uneven in the level of, like we're gonna get even, but I just tricked him for about 5 seconds, and he tanked my career, right? Or tried to. And then he understands, and I joked with him, and it's like, well, I'm gonna give you negative reviews, and then he knows that that's an empty threat because we'd be screwed without him. So he's just like, fine. He's like, fine, I'd make more money in the real world anyway. I was like, fuck. I was like, shit, you're right. Sorry, I apologize. Yeah, apologize. Okay, how about this? Let's do this and this is maybe, let's do this right now. Solve this symbolically.
Is that not what we're doing?
No, this is all numerical, right? This is numerical ordinary differential equation solver. So solve this and make the same plots using the symbolic toolbox. That'd be a little exercise for you. Because we learned how to use the symbolic toolbox last time, and you'll use that on your homework next time. Go back to the previous one. I will do it independently up here, but I'll mute it so you can't see.
I have a feeling that symbolic is going to be way easier. I doubt it.
Dominant declareth.
Mike Berry is malevolent.
And Tim White is benevolent.
It's benevolent.
That should be better.
We don't even need to do the weird line stuff. Just go straight from X. I'm on to you.
Symbolic, we go. You can define your sims. Symbolic can handle second order differential equations, by the way. Oh, you're not supposed to be looking at this. I thought I muted this. You sons of bitches. Yeah, that's shit. I was like, what are you gonna do? I thought you were doing it. Yeah, sons of bitch. I hit mute. It didn't work. It muted the sound. You couldn't hear me. Yeah. You couldn't hear me breathing. Couldn't hear me breathing and typing up here. Oh, yeah, I did it. I did it.
One better.
I don't really know what it is.
Yeah, except Mike's should have been faster.
Seems like it worked.
This is the opposite of that.
Yeah, well, I can't plot it because I'm
Stick button. Not half. 6 keys. What happened? Uh-huh. Actually, more than 6 keys tab also. Just outage. Oh, this is oh, that's they did it.
Oh my god.
You're first.
Did you get it?
Nope, but I see it. Did you see the dot?
Yeah, this is What was your speed on that? Yeah. Oh.
Oh damn. Does this actually say what the union is not?
Ha. It did it.
What am I supposed to do after I make the equation?
You do it. Plot it. Yeah. So you got to give it values of M, B, and G. So if you use the subs command, you can put M, B, and G in there, and then you can plot it and see if it matches the. Yeah. That's what I'm doing right now. I'm just making sure that it works.
This way.
By the way, this is exactly what you do on your homework. You're going to do a numerical solution, and then you're going to do the analytical solution, and then you're going to plot them and verify that it's the same.
Error in.
So
It's not giving me the right.
you're going to get an F then. You're going to get an F.
Isn't it? Is this the extra credit one?
No, the extra credit one's way fancier. But it's like this, but it's fancier.
Um. That's weird. Why is this giving me like 40,000 errors?
That you made mistakes 40,000 times.
They're like, it's giving me errors about the internal functions for this bug box. So they don't need.
Because you've done something wrong.
Yeah, but how is this helpful? MU pad engine.
If you trace it back up, it'll show you where you made the mistake.
In this guy.
It says. Oh, you gotta say what B is. Oh.
Oh, so he's not in here.
Yeah.
Here's A.
Correct.
But that's what I'm defining it here.
No, I know, it's not a pricing. It's I'm staying up too late on my phone. It won't be charging.
Oh, it's gotta be equal to something. Oh, you got it down here. Oh, you use equal to 0. It's the same thing.
Oh, there's an X. Is that the only?
Yep.
Wowza.
Okay.
Okay, so now
We do anything, Connor? Did you get it?
I have to U2 of T equals subs U2.
Sims, X and T, M, B, and G, M is 1, B is. Oh, no, you leave those as variables. You want to leave those as variables. So yeah, you want to just symbol it. Later on, we'll define those at the bottom, but that's. Okay, yeah, so there's your equation, right? And remember, if you can't. So you have to make it equal. Right, you can't set equal to, right? Because then it replaces what we have them stored. So that's just basically an equation. And then the way the D-solve works, without the initial conditions, is just.
Yeah. I use my computer a lot. I can't afford to not have it. I don't have a desktop.
Should you should have constant.
It's F plot.
Summer,
U2.
or whatever.
I give you the short
But I just put it away. Not thinking about you for the next 3 months.
Right, so then there's the answer that has the constants in there. You can add in just additions too.
No, I do it. It's just the umbrella term. It's just like the first derivative.
Oh, Eureka!
You guys are sitting up here just done.
Not even try it.
Why his computer, which is 2 years newer than mine, is slower.
It doesn't rotate anymore.
Right, you want that? Zero.
Did you guys even do this in one?
No.
Come on, man. Come on, man.
And then that's like you have to put those.
You guys not your symbol?
I also haven't skipped this class to do timber homework, so.
True. That was Congress.
Actually, if we put in those
I did timber homework in this class,
I've done that.
but I didn't skip it to do this.
That sounds dangerous.
So that's the thing. And now at this point, now that you have it, you could put in you put in GE and MR, and then you spawn. And then you should get the same answer exactly what we had in this place. See, are you getting it? Man, look at that, huh? Yeah. So that, yep, and then so that has the constants there. C1 and C2. Or you could do the difference. Or you just put it, or you could do comma 2 where it says just second. Yeah, but I think that works, right? It sure looks like it worked. Yeah, I agree. Yeah, that's right. Yeah, you can do it that way, absolutely.
But then
Yep.
Oh, yeah.
Yeah, I put it in the
It's just
D-sol.
the
And then what you want there is that x of 0 be 0. That means it starts at 0. And then v of 0 is equal to 0. And so you have to set up what v is first. V is the derivative of x. And so once you do that, then right in here, right after
Yeah, that's what the choice
right there, you do comma and then a square braces, and then say x of 0 is equal to 0, and v of 0 is equal to 0. Yep. But set up v first, and then you'll do that right above where you do the d sub. Yep.
That's true. There was the dry unit weight one.
Nothing? You got nothing over here?
We were trying to figure out why my kids are slower than him.
It's slower processing than mine.
And then I was trying to figure out why my keys still don't work.
Hey, both of them.
Both of them was both with Intel chips. One's just a better Intel chip.
Well, if that's how Mike did it, then I guess he's right.
The only difference is I have an HDD and an SDD. I think it's just an SDD.
You have a solid
Oh,
state.
solid state. Those make a big difference, solid state drives.
We don't have them.
Yeah.
Oh, I just have a
Also had
You have a spin-in.
Yeah.
Oh, you do. Yeah, you should be way faster than this.
Yeah, I don't know.
Is it close? Increase the number of times it counts, and maybe it's. How we doing over here? Gavin, you paying attention unlike these two over here?
Yeah, we're trying.
Yeah, good. Thank you for trying.
Jump here to
Getting far, but
We're trying.
Okay.
Do a lot.
We gotta to make the equation.
Yeah, you got to make the equation. That's great.
So now we have.
Well, that's
D-sol.
gonna be a lot of-
Is the command.
Why did you?
Yeah, you just do it because you're solving that differential equation.
Don't you put values in for it?
Yeah, but you can do it without, say, just try without that. Just do
Yeah.
D-solve, and then your equation equal to 0. So you gotta go equals 0. Right? Because unless you have it up above, I don't think you have it up above. Yeah. Then, so I'll give you an answer. Right, look, almost, there's the answer. That's the answer. But what you're missing is what C1 and C2 are, right? Wait, and that comes from adding in your initial conditions. And the way you put right, and so that's it, right? You know, you take this as secondary, you need to give it 2 initial conditions. The initial conditions are that x is 0 and the velocity is 0. Right? That's what you have to do. So basically what you do is just
Why
right
is
here,
that?
Gavin.
So you're like UT equals D solve, and you do like the initial conditions. And that would be the equation. And then you
And then you
sub
put your initial conditions right.
substitute your.
And that's just your.
So you do literally you type x of 0. So like open 0, yep. And then comma v of 0.
Yeah, that was like, that's how I did it first.
It's equal to 0. So you gotta go equals.
I'm like,
On each
trying to look
one.
at that example.
Yep. And then you go back to this. And so this isn't gonna work.
So how does
It
it go
just
with
like.
these?
You don't. So I was gonna say it's gonna kick out an error and say I don't know what v is. And so up above there, you just said you say v of t is equal to diff x of t. And so you define v of t up above. And then that should do it.
Okay.
Give that a go. Thank you two for paying attention and trying. Did you guys work? You paying attention to trying? You guys paying attention to trying?
Oh, yes. How do I?
Yeah.
Oops.
You comma,
This is such a
and then
cheeky little
open
thing that I'm
square
doing.
braces,
Oh my God.
and then close square braces, and then in between it you do x of 0 is equal to 0, and then v of 0 is equal to 0. And then when I say equal to, it's equal equal. Right? Yep, you're saying you're comparing. So yeah, so go. Yep, that's right. And then you'll do v of 0 is equal to 0. But you gotta define what v is first. So up above, you just say v is equal to if x of t. That's it. Yep. If x of t is and then right there you say v of 0 is equal to 0. It might automatically do it for you, maybe. Yeah, it wants you might have to do that. You might do v of t as a
That'll happen.
that should do it, because then that will knock the C1 2 off.
That's so funny.
That's fine. Yep, I'll show you that way. So, I'll show you that. You do sum the equation, and then you put the three things you want to sum, like m, g, and whatever, and then you do a column, and you put them all in a row. Then you square
Do
braces.
it. These kids are soccer fans. They know
What was
what's
the error?
up.